25. In this lecture, we will define a new concept called strongly connected component, and then we will describe an algorithm to find all the strongly connected component, abbreviated as SCC, of a graph in linear time. So the graph that we assume as the input is a directed graph, and it may contain cycles. Okay, so let G be a directed graph for two vertices u and v. If somehow u can reach v by using a directed path, and then v can also reach u by using some other directed path, then these two vertices are called mutually reachable. And then we will use the symbol u, this arrow. So there is a two-pointed arrow like this to represent u can reach v, and then v can reach u. So here we have also a simple assumption that we assume that for each vertex itself, it can reach itself. So it is mutually reachable to itself. Okay, now we can easily show that this mutually reachable is an equivalence relation. So an equivalence relation has the property that u is related to u for any u. If u is related to v, then v is also related to u. And finally, there is a transitive relation, like u is related to v, v is related to w, implies u is related to w. So we can easily check that this mutually reachable idea is an equivalence relation. And because of this, then this particular thing, this relation, can be used to partition the vertices into groups, okay? Or more formally, each group here is called an equivalence class, okay? And then what do we mean by this? It is like u and v, they will be in the same group if and only if u and v are mutually reachable. So by looking at the induced subgraph of each group, then we get a so-called strongly connected component. So here, let us see an example. So we have the input graph. Forget about this dotted line at the beginning. The input graph has 8 vertices and a couple of edges. So here, we first see that S can reach W, S can reach R, and then R can reach S, R can reach W, and then W can reach R, W can reach S. So we actually can see that all these 3 nodes, they are mutually reachable to each other, right? So in that case, these 3 nodes altogether, they form a class or a group of vertices that we have. This is a strongly connected component. In contrast, V itself can only reach V, although it can also reach R, but R cannot reach V. So V and R, they are not in the same strongly connected component. So V is only mutually reachable by itself. That's all. So in that case, V itself forms a strongly connected component itself. And then we also see that all these 4 nodes, U, T, X, and Y, they are mutually reachable to each other. So in that case, these 4 nodes, they also form the same group, and then it is another strongly connected component. So notice that in this graph, we have partitioned the vertices into 3 groups. Okay, each one of them is mutually reachable to each other. Okay. Now, there is an interesting property about this SCC idea. Suppose that we reverse the direction of each edge of the graph G. So after doing so, we will obtain a different graph. Let's call it H. Notice that this graph H will be defined on the same set of vertices. Only the directions of the edges are reversed. Then we can see that whenever U and V, they are mutually reachable in the graph G, then it must be true that U and V are mutually reachable in the graph H, and vice versa. So because of this, the SCC, if we only think about SCC to be, rather than the graph, SCC is corresponding to the partition of the vertices. So each SCC, let's say it is represented by the set of vertices inside, then in that case, each SCC in G will have a corresponding SCC in H. And they are based on the same set of vertices. Okay, and then here we have defined the concept of SCC, and let us see, once we are given an input graph G, directed graph G, can we find out all the SCCs corresponding to G? Now from the previous result, this is the previous result, we find out that the SCC of the original graph G will be the same or will correspond to the SCC in the reverse graph H. So if we want to find all the SCCs of G, it is the same as we find all the SCCs of H. So our basic strategy for this problem here is that somehow, while H contains some unvisited vertex, we will pick a vertex X and try to find out all the vertices in the same SCC as X. And then we will visit all the vertices that is found in line 3. So this is our basic strategy. So somehow we have this graph. Let's say we get the reverse graph. Let's see if we have an example of what we are going to do. So basically we get a graph G, get the reverse graph, and somehow for some reason we can find out starting to visit some node X, and then somehow at that time we can visit all the SCC, all the nodes in the same SCC as X, and then in that case we can extract the SCC corresponding to X, and then we can do so one by one. We will be able to output the SCCs of H one by one. So this is the idea. Okay. But then in order to make this process efficient, we will need to find a way to select X carefully so that finding all the vertices in the same SCC of X can be done quickly. So by choosing different X, we may have different time to find out or checking whether the vertices are in the same SCC of X. But if X is selected carefully, then we maybe do this part easily, and so that the overall running time will be fast. Okay, to help us to do this selection process, we want to have more understanding on the properties of SCC. So let us continue our property finding. Okay. Here we are going to introduce a new concept called component graph. So what do we mean by this? Okay, so remember we start with a graph G, and somehow given the graph G, using the mutual reachability relation, we will be able to classify the vertices into groups. And now suppose that we contract each group of vertices into one single vertex. So we are doing the contraction. So here in this diagram, we are contracting V into a single node. So it is now represented by V1. We will contract all the three nodes here, RSW, into a single node, and it is now represented by V2. And we contract the four nodes here into a single node. It is now represented by V3. We will still keep the edges from this component, this node to this node. So there is an arrow here. So this arrow represents this one. But here we will see that there are two arrows pointing from red to green. But here we are doing this for simplicity. We will just keep one arrow so that we will keep the resulting graph a simple graph. Okay. We will also remove loops if there are any. So in that case, by contracting each SCC into a single vertex, we get some new represented graph. And this is called the component graph of the original graph G. So each vertex corresponds to one SCC in the original graph. So we have three vertices, three SCCs. Okay. Now we can easily show that the component graph of the original graph is acyclic. So here we will see that it is still a directed graph, but then now in this graph, we want to show that there is no cycle. Okay, so we are going to show this by contradiction. So suppose to the contrary that this component graph is cyclic. So in that case, inside the component graph, there are vertices Vj and Vk such that Vj can reach Vk and then Vk can go back to Vj. Yeah, because it is cyclic, so there is a cycle, right? Now, if this is the case, so for instance, this is cyclic. So for instance, V3, there is an arrow that points back to V1. Now, in that case, let us examine what happens in the original graph. So remember, each single vertex here represents a bunch of, possibly a bunch of vertices in the original graph, but they are mutually reachable. So this corresponds to a bunch of vertices, this corresponds to a bunch of vertices, and this also corresponds to a bunch of vertices. So if Vj and Vk, they are mutually reachable in the component graph, then the corresponding component, big Vj and big Vk, a bunch of vertices, will now be mutually reachable because any vertices in Vj are mutually reachable, and for some vertex, it has a connection to some vertices in Vk. So in that case, all the vertices in Vj can reach all the vertices of Vk. And similarly, Vk is mutually reachable to Vj. So there is some vertices in this, a bunch of vertices of Vk that goes back to Vj. So in that case, any vertices in Vk, big Vk, can reach any other vertices in Vj. So in that case, Vj, Vk, here, these two big groups of vertices, they are mutually reachable to each other. And then this gives us a contradiction because of what? Because they are all mutually reachable, so they should have been classified as in the same SCC from the beginning. So why we have two of them instead of a single of them? So this is a contradiction. This contradiction gives us the fact that the original assumption that the component graph of G is cyclic is wrong. So in that case, we prove that the component graph of G is always acyclic. Okay. Okay, now this is the first property. So let us take a look of another property. So here, this is the component graph of G. And assuming that we are reversing each edge of the original graph G to get a reverse graph. So how will the component graph of this reverse graph H looks like? So we will claim that it must look like this one. So this is the reverse graph. So it will still have the same vertices because each vertex corresponds to a corresponding SCC, and then G and H will have the same SCCs. So the component graph of G and the component graph of H, they are also defined on the same set of vertices. But since the arrows are in the reverse direction, so when we have an arrow like this here from V1 to V4, then in that case, for the component graph of H, the arrow will be reversed. So it is rather simple. So we get this component graph of G, and by reversing all the arrows in this component graph, we actually get the component graph of the reverse graph of G. Okay. Okay, now let us consider the following question. Let's focus on this particular example. Let's look at this V1. So V1 in this component graph does not have any outgoing edges. And V1 may correspond to a bunch of vertices in the original graph. Now suppose that we pick a vertex, let's call it X, inside this group of vertices of V1 and then run BFS on this graph, on the original graph. Then what will happen? Yeah, on the original graph H. Okay, so H here, this is the component graph of H. So expand this as a group of vertices and then run BFS on this vertex X in H. What will happen? Then we will see that because all the nodes corresponding to this little v1, they are mutually reachable to each other. So when we run BFS on the source vertex inside here, this group of vertices, all the vertices will be reached by x. But however, that's all the vertices that x can reach, because all the other vertices, they are now, there is no way that we can go out from this SCC. So this is the summary. We will visit exactly those vertices in the same SCC as x here. And so this property not just holds for V1, it also holds for V6, because V6 here, it also does not have any outgoing arrows. So in that case, if the source vertices comes from a vertex inside the component of V6, then after the BFS, we will only visit exactly the vertices here in this group. So this gives us a refined strategy of our original method as follows. So here, while H contains an unvisited vertex, we will pick an unvisited vertex X inside an SCC such that the corresponding vertex in the component graph has out degree 0. So this is how we pick. We can pick a vertex in V1. We can pick a vertex in V6 in this example. After that, we will run BFS on this. And after that, all the vertices here will be visited. Okay, and then here, if you run BFS here, then all the vertices here will be visited. So we will repeat this process each time. We will visit all the vertices in a certain SCC, and then we repeatedly find an unvisited vertex. So for instance, if we pick luckily a vertex in V6, then we will visit all the vertices here, and after that we may pick a vertex in V1, then we will visit all the vertices here, and after that we may be able to pick a vertex at V4, because at that time V4 will not have any outgoing arrow, because V1 are now all visited. So this is the idea. Okay, so here the problem here is we need to find a vertex X that is located inside an SCC without degree 0. So how do we find such a vertex X? So basically, we are claiming the following result based on DFS of the original graph. So if we perform DFS on the original graph, the vertex that has the last finishing time could be used as a candidate vertex X. So in particular, this vertex U with the last finishing time will always be in an SCC whose corresponding vertex in the component graph of H has out degree 0. Okay, so this is what we want to show later. And actually equivalently, so this is about component graph of H. Okay, so if we go back and reverse the arrows in our mind, then U will be in an SCC whose corresponding vertex in the component graph of G has in degree 0. So this is something the same here. Okay. Okay, now suppose that this claim is true. Then we now have a way to find a vertex U or the corresponding vertex X that has a good property. So this is how we can refine the algorithm. So first of all, we simply run DFS on the graph G, and we also get the reverse graph H of G. Okay, and we set all the vertices as unvisited at the beginning. So this time, although we have run DFS, at this moment we will reset the graph. Yeah, we are going to run on the reverse graph H. So we will reset all the vertices as unvisited, but we record the DFS finishing time after we run it on G. Okay, so this is the setting. So after line 1, we have the finishing time on all the vertices based on the DFS of G, but after line 2, all the vertices are now becoming refreshed, so they are unvisited. So while H contains an unvisited vertex, this time we will try to perform perform the SCC finding. So what we do here is we pick an unvisited vertex U with the latest finishing time. So this finishing time is according to what we have done in line 1. Okay. Once we got this vertex U, we will apply BFS with U as the source to run it in the reverse graph. So after that, we make all the vertex in the same SCC of U visited. And this gives us the idea of somehow all the vertices are now becoming visitors, so they are conceptually removed from the graph of H. So H will now continuously find another unvisited vertex, and then this time we will choose from the remaining vertices which one has the latest finishing time, and then this one will now be in an SCC that has no outgoing arrows in the component graph of H, and we will repeat the process and then extract another SCC again and again. Okay, so if we can see this, then the total time for this algorithm is just V plus E because we are applying DFS, and here this is again a bunch of BFS altogether proportional to the number of edges in the corresponding SCC extracted. Okay, so all the running time here in total is V plus E. And actually, we can exchange the role of G and H and then describe the method in a symmetric way. This time, if you understand everything so far, then we can now exchange the role of G and H in this way. So we first get the reverse graph H of G, but this time we run DFS on H. So the DFS is run on H, and now the extraction of the SCC is done on G. Okay. So we run the reverse graph, get the DFS order, and then when G has an unvisited vertex, we pick a vertex U with the latest finishing time during the DFS of line 1. So again, we can apply this and extract the SCC one by one. So in total, the running time is order V plus E. Okay, so what remains is we want to prove that the node, the vertex U with the latest finishing time, is always in an SCC such that its component graph vertex does not have any outgoing arrow. So this is the claim that we are missing. So we want to show why it is correct. And to show why it is correct, it is sufficient if we prove the following theorem is true. Okay. So let's take a look at this theorem. Okay. So consider running DFS on the original graph G. So we are referring to this method. So we run DFS on G. Okay. So, and suppose that there is an edge VW in the component graph of G. So what does that mean? It means that V will not have, sorry, it means that V will have some, so there is an edge WV in the component graph of G. So here, this is strange, okay, but then this is true, okay. Suppose that there is an edge in WV in the component graph of G. So what does that mean? Okay, so that means that in the component graph of H, then there is an edge from V to W. Is that okay? So basically, this theorem says that if there is an edge from from W to V in the component graph of G, then the last finishing vertex of the DFS running on G cannot be located at V. So when V has incoming arrow in the component graph of G, then V cannot be the last vertex. So equivalently, when V has outgoing arrow in the component graph of H, then V cannot be the one with the last finishing vertex. So as long as this theorem is true, the last finishing vertex must be in an SCC such that the corresponding vertex in the component graph of G has no incoming arrow, or the corresponding vertex of the SCC in the component graph of H does not have any outgoing arrow. So hope that you are all okay with this one. So we are going to prove based on every argument on G here instead. Okay, run DFS on G. If there is an edge WV in the component graph, then G cannot be the one with the last finishing time. So let's prove this claim. Okay, if this claim is true, automatically the previous method works. Okay, so let's go ahead with the proof. Okay, so here suppose that there is an edge WV in the component graph of G. Okay, so here this is an illustration. Inside, so this is the component graph of G. So we have W pointing at V. Is that okay? Now, in the original graph G, then W corresponds to a bunch of vertex, V corresponds to a bunch of vertex. So we have SCC corresponding to W, and then SCC corresponding to V. So there may be vertices, more than one vertex inside. And here we let X to be the first vertex in this SCC visited by the DFS of G. Okay, and Y be the first vertex visited here, and Z be the last vertex visited here. Is that okay? We actually want to show that the vertex with the last finishing time cannot be this Z. Okay, so the last finishing time vertex cannot be inside this component. Okay, so why? Okay, so let's see. So there are two cases. So we have X and we have Y. They both represent the first vertices visited in the corresponding SCC. So if X is first visited, by the time that X is visited, all the nodes in SCC of W here are white. All the vertices in SCC of this V are white. And then because there are mutual reachability of vertices here, and then there is an edge that goes here, and then they are mutually reachable here. So in that case, X can reach Y using white paths. So in that case, we will, and X can not just reach Y, X can also reach Z. Okay, so by the white path, we have X, Z, Z, X. Okay, so in that case, we have this one. And then another case, this time when Y is visited first, then what will happen? Then in that case, because SCC of V and SCC of W, they are different. So in that case, all the vertices of this SCC V has to be visited before SCC of W can be visited. Otherwise, that will mean that we have a cycle, and then these two SCCs should be the same. They are all mutually reachable. So in that case, it cannot happen. So in that case, when Y has discovery time less than X, then all the vertices inside this group has to be done before this one. So again, we will have f of z. Z has to be finished before X can ever start. So in any case, the finishing time of Z is smaller than the finishing time of X. So in that case, Z here cannot be the one that is finishes last among all the nodes in the DFS order. So in such a case, we have proven the claim, and so that's all. Okay. Now to fully understand this concept of SCC, so it is actually not difficult. So you can try to apply this algorithm on some small graphs, and then get the feeling why it is correct. Okay, so that's all for this lecture 25. Thank you.